I would now like to talk about a test to see whether a series diverges. So first, let's let S sub n be the sequence of partial sums, sum from k equals 1 to n a sub k. And let's suppose that the infinite sum converges to S. Well, by definition, that means that the sequence of partial sums converges to S. So the limit as n goes to infinity of S sub n is equal to S. Now, I'd like to see what happens to the individual terms in the sequence. So in particular, I want to look for what happens to S sub n minus S sub n minus 1. So S sub n minus S sub n minus 1 is the sum of the first n terms, sum from k equals 1 to n of a sub k, minus the sum of the first n minus 1 terms, the sum from k equals 1 to n minus 1 a sub k. So if I take the first n terms and subtract the first n minus 1 terms, what I'm left with is the last term. That term is a sub n. So we can think of the last term as being the difference between two partial sums, the nth partial sum and the n minus first partial sum. So how is that helpful? Well, we can then ask what happens to the individual terms in the sum. What is the limit as n goes to infinity of a sub n? Well, we just saw that a sub n is in fact the nth partial sum minus the n minus first partial sum. So we can take the limit of that. But the limit of S sub n as n goes to infinity is S. And likewise, if we just take one term less, but let n go to infinity, then the limit as n goes to infinity of Sn minus 1 is also S. And so that says that our limit of our terms within the sum, a sub n, is equal to 0. What this is saying is if the sum converges, the individual terms must go to 0. Now, what if the terms did not go to 0? What if, for example, the terms went to some other number, like 1/3? Well, then the sum from k equals 1 to infinity of a sub k, well, it would look like a sub 1 plus a sub 2 plus a sub 3, and it would keep going out to some nth term. And then finally, it would start looking like essentially 1/3 plus 1/3 plus 1/3 plus 1/3. It would be adding 1/3 over and over and over again to the tail end of this sum. And so that sum would go to infinity. So if the terms go to some positive number that's not 0, then the sum would go to infinity. Now, we could take the terms and have them go to a number like negative 1/3. So what would happen, though, is that in the tail end of this sum, we would keep subtracting 1/3 over and over and over again. And so this sum would end up going to, say, minus 1 infinity. So if the terms converge to some negative number, then at the tail end of the sum, we would be adding the same negative number over and over and over again, and it would go to negative infinity. So in fact, what we have now proven is what's called the nth term test. And that says that if the limit of the terms approaches a number that is not 0, then the series diverges. So in this sense, there is no hope for the series to converge if the terms do not go to 0. What's important to understand, though, is that this is a test for divergence. Okay, so this is the nth term test for divergence. It is not a test to see whether a series converges. It's a test to see whether a series diverges. So the converse of this statement is false. If the series, or if the terms go to 0, that does not say whether the series converges or diverges. Because, for example, the harmonic series, okay, it diverges, as we've seen in the past, even though the terms go to 0. So we've seen sums like this, of the sum of 1 over k that diverges, even though the terms go to 0. But we've also seen, at least numerically, that the sum of 1 over k squared, in fact, converges. And so knowing whether the terms go to 0 does not tell us whether the sum converges. But if the terms do not go to 0, then the sum diverges. So what you would do if you're trying to test to see whether a series converges or not is the first thing you would do is just look at the limit of the terms in the sum. Okay, so I would look at the limit as k goes to infinity. For example, in this problem where the terms are 1 plus 1 over k squared, and I would see that that limit is equal to 1, which is not 0. And so that would tell me that the series diverges. If I keep summing up the terms, as I'm looking at the tail end of the series, I'm adding 1 to the series over and over and over again. And so the series would approach infinity in that case. Now, if we take the limit as j goes to infinity for this next sum, the sum of j over 2j minus 1, we see that the terms go to a half, which again is not 0. And so that would tell me that that series diverges. Finally, we could look at, say, the limit as n goes to infinity of the terms in this next sum, which is n plus 1 factorial over n factorial. We would have to simplify that. N plus 1 factorial is just n plus 1 times n factorial, and that's divided by n factorial. We see that those factorials cancel, but the terms go to infinity. And of course, if the terms do not go to 0, the series diverges. So this gives us a plan that we can follow when we test to see whether a series converges or not. First, just ask the question, do the terms go to 0? And if the terms don't go to 0, then the series diverges. Second, if the terms do go to 0, then we need to do further analysis. So for now, we can just use this test to show that series diverge. Okay, let's do one more example. So I want to show you how to use partial fractions, which we looked at as an integration technique, to show that a series converges. So I'm going to have a series whose terms look like 1 over j times j plus 1. Well, that can be broken down as the sum of two fractions, a over j plus b over j plus 1. Now, if I find a common denominator of j times j plus 1, then that would tell me that a times j plus 1, or that would equal a times j plus 1 plus b times j over j times j plus 1. So that tells me that, let's say, a times j plus 1 plus b times j would have to equal 1 in the numerator. So that says that a plus b must be 0, and that also tells me that a must equal 1. So I can now solve for b, which is equal to minus a, which is minus 1. And so I can say that 1 over j times j plus 1 is equal to 1 over j minus 1 over j plus 1. So what I want to do is I want to substitute that into a sequence of partial sums. So my sequence of partial sums is going to be the sum from j equals 1 to n of 1 over j times j plus 1. But now I'm going to substitute in what I get from partial fractions, which is 1 over j minus 1 over j plus 1. Now I'm going to write out what some of these terms look like. It's 1 over 1 minus 1 over 2, plus 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, etc. Until finally I get 1 over n minus 1 over n plus 1. In fact, I'm going to add one more term here. Just to emphasize, this would be plus 1 over n minus 1 minus 1 over n. And so this is one of those telescoping sums where we see that the middle terms cancel. So the halves cancel, the thirds cancel, the fourths cancel. Okay, 1 over n minus 1 cancels with something before it, and the 1 over n's cancel. And so the sum collapses like a telescope, and I'm going to get 1 minus 1 over n plus 1. So now, if I look at the limit as n goes to infinity of the sequence of partial sums, I get that that limit is 1, and that tells us that this sum in fact converges, and it converges to 1. Now, something that we did previously was that we approximated an infinite sum using the first n terms in that sum. So sometimes we might want to look at a sum and we might want to approximate this sum by just summing the first n terms, where n is some large number. And when we do that, essentially what we're saying is S is approximately S sub n. So what I want to know is, what is the error in making that approximation? So the error would be S minus S sub n. So what happens when I say use 1,000 terms to approximate this infinite sum? Well, in this case, what I can do is I can substitute in the formula for the sequence of partial sums. So looking back, I can substitute in that formula, which the infinite sum was 1, and then the sequence of partial sums was 1 minus 1 over n plus 1. And so the error in the approximation is just 1 over n plus 1. So, for example, if you approximate the sum S by, say, the first 100 terms, so I just add the first 100 terms, the error is about 1 over 101, which is about 0.0099. And so that's an important thing to note, because there are some infinite sums that we're not going to be able to find the exact value of, and we're going to want to run an approximation. And if we can get a sense of how accurate that approximation is, then that gives us a sense of how close that our approximation is to the infinite sum.